and the slideshow from the current slide. And let's go over just a few things. I feel really terrible on this first one. Today will be a short class. Sorry about that. Sort of a long and strange story, and you probably don't care to hear it anyway, but my wife's birthday is coming up, and she wanted to go see Steve Martin and Martin Short. Y'all are probably too young to remember who they are, but they're pretty good comedians. We heard they were coming to Birmingham, so that was
Who is it?
Steve Martin and Martin Short.
Is it still alive?
Yeah, both of them. I guess. I hope, because we paid for tickets.
I hope so.
Yeah, and so my wife got tickets for it. I was just under the assumption it was a Friday night or a Saturday night, sometime like that. And then when she said, "Oh yeah, we got the tickets," so when, what weekend is it? She said, "Oh, it's not the weekend, it's Thursday night." I said, "What?" But she had already got the tickets, and they were, I think, fairly expensive. And it's her birthday, not yet, but coming up. So anyway, I've got to leave early tonight because otherwise I'd miss the show, and I'd be in the deep dog house. Okay, the outhouse of the doghouse. Okay, so anyway, so we'll get going and go as much as we can. There will be no lab today. Okay, first time I haven't had something to grade from this class ever. So all right. Let's go over a few other things. I still, at this late date, have only received uno research paper. There's the second one. Okay.
How many words?
What's that?
How many words or pages do you want?
It's 1 to 2 pages. Yeah. 1 page is not enough, something between 1 and 2. You can go over 2. That's no points off of that. But if it's less than 1 complete page of text, you will lose points.
And how many sources would you like?
I'm sorry?
How many sources?
At least 1, 2 or more are better, okay? Because it's a short paper. So get it to me when you can. Okay. You did hear that it's word processed. Did you hear it was word processed page of text?
Word.
Well, I don't care which package you use, but it just needs to be word processed, not handwritten.
So I need to print it out?
Yes, for me to read it. Yeah.
You can read this.
Well, it'll lose some points. Do you mind? You don't mind not losing points? So you're going to turn it in that way?
So how much it will lose?
Well, I'll decide that when I'm grading it.
There's instructions on Blackboard how to do it.
What's that?
You have instructions on Blackboard.
Yeah, and we did them at the first of the term.
APA.
Went over in gory detail. You could have listened to them on the
Or if you
power. Yeah.
If he wants to do it, I will let you use my computer or.
No, I have my computer. I don't have printer, that's why.
Okay, well, you can bring it to campus and print it. I mean.
It's the last day to get bonus one.
Well, tomorrow is technically the last day.
But I don't have classes tomorrow.
Well, I'll be here though. So.
But I live in Trustville.
Huh?
I live in Trustville.
Okay, well, whatever. You can either turn it in or not turn it in. It's up to you.
But you say how much it will lose, if you estimate.
I'm not going to grade it right now. Okay, either turn it in or turn it in later. I don't care. Okay.
So this will lose a point.
I'm sorry.
For sure.
I'm sorry.
This will lose a point.
Oh, for sure. Because it's supposed to be word process.
Okay.
It was in the instructions. Okay. All right. Okay, so I've only gotten 1 paper in so far. Please get your papers in. And today and tomorrow are the last 2 days to forfeit that, that you can still get that 1 bonus point. And if you get them to me anytime next week, you just get your score. And, okay, we'll talk about the rest of that later. Okay, I went through with you before on what labs I'm missing. I'm still missing at least 1, either lab or test, and not the same people, but different ones. A bunch of people did turn in some things today, but I haven't had a chance to grade them and find out what's still missing. So please get caught up with your labs and with your test if you haven't already. Okay. Now, let's talk about how we're going to go from here. We're going to continue in chapter 6 today. Okay? I'm sure we're not going to finish it today, but we will continue. That means on Tuesday, hopefully we will finish chapter 6, at least get far enough to have the last lab in chapter 6. Okay? Which means, more than likely, we will have the test of chapter 6 on Thursday of next week. Now, we'll get started on chapter 8. Hopefully, if we finish chapter 6 on Tuesday, we'll get started on chapter 8. Continue that on Thursday. I don't think we'll get far enough for a lab. We might, but I doubt it. We only have one lab for chapter 8. So the odds are on Tuesday of the following week, that's technically our last day of class. If we haven't finished up chapter 8, we'll finish it then. If we have already finished chapter 8, you'll have the test on chapter 8 then, because we have the test on chapter 6 probably on Thursday of next week. So, and the odds are we'll be doing the lab for chapter 8 on that Tuesday. After that, we're done with the material for the course. We'll still have the chapter 8 test to go and the final exam. So, those are technically, it just depends on when we finish things, and Stephanie is here.
So I'm writing down December the 6th is the test.
Second?
December the 6th is the test.
Is which test?
The next.
Okay, going for this chapter. Yeah, that's Thursday of next week. Right. And then more than likely, the following Tuesday will be the test on chapter 8. Or at least the lab on chapter 8. If we finish it on the 6th, then we'll have the test on chapter 8 too. We'll just see how far we get. Okay? And if we get far enough that you can take the test on chapter 8, then the final is technically scheduled for Thursday. And there's Michael. Okay. It's technically scheduled for Thursday, 2 weeks from today. Now, at least one person, I believe it was Dalton, said that he was going to be out of town that day, so he wanted to take his early. And it just depends on how things pan out, when he can take that, but he said he'd be available Wednesday. So if any of the rest of you want to take it early, we'll talk about that next week and Tuesday of the following week. But I'm pretty sure that that can be done because I'm going to let him do it so anybody else can do it as well. All right. Any questions on how we're going to wrap up things? So what we have left to do is one more lab in chapter 6, the test for 6, one lab for chapter 8, and the test for chapter 8, and the final exam. And I think you'll find the final exam is one of the easiest you'll have all term. It's
The final exam is going to be
Thursday, a week away, 2 weeks from today. 2 weeks from today.
That's the 13th, I guess.
Right. And if you need to or want to take that earlier, once we get all the material covered and done, anytime after that point, and we'll talk about this as it gets there, you can take the last test and the final. Okay? All right. Any questions? All right. Let's hit where we left off before, and actually, my mark in the text. Oh, and let me also tell you this. I mentioned the fire on the Birmingham campus. Here's one direct ramification of that, okay? The office where I usually work on the Birmingham campus, from what I can tell, is, I don't think it was damaged any, but they say the building stinks of smoke and that everybody has moved out of that building. They're not letting anyone in that building until they get it all cleaned up. So that means I'm coming here tomorrow. I'm not going to the Birmingham campus. So therefore, if you do want to turn in a test, I will be down in my office from 8 to 12 tomorrow. Okay? Now, if I find out there's some need I have to go over to the other campus, like they call a meeting or something, that may change. So far, I don't know of anything like that.
Is it possible to make up a lab tomorrow?
Yes, it certainly would, especially if. And Stephanie? I think he's trying to remember that. Okay.
Sorry, I was calling her all night. I was calling her sister. No.
So, I will be, as far as I know, I'll be on this campus tomorrow. All right. Any questions? Okay. Let's get going then. The last thing that I had that we were doing, we did not have a chance to do example 6.3 at the top of page 152. Okay? And this was still dealing with basically, it's still dealing with electrical resistance. So this, sorry. I know what I was doing now. Y'all missed the slides from last time because I could not get my computer to read PowerPoint. It said it wouldn't read a PowerPoint file. It couldn't read a PowerPoint file. PowerPoint couldn't read a PowerPoint file. It makes no sense. Today I came in fact, shortly after my other class finished, I brought the stuff up here. It loaded like a champ. I don't know what happened on Tuesday. Here are the slides you missed, just so you'll be able to go back and watch them in Screencast-O-Matic or on YouTube videos. This was the one on the force field. You can listen to what I talked about it on the one I recorded Tuesday. Here's the PowerPoint slides from that. Okay? And we talked about all this before, so, and it's Stephen? Okay. Now, remind me, do you go by Steve or Stephen? Stephen? Okay, got it. That's what I was thinking, but I couldn't remember. All right, I've got necessity here. Okay. All right. So here are the slides. That's all I'm doing here is showing the slides from last time. Okay, I'm not going to talk about them again. That was remember my illustration, waving my arms, two positive charges, a positive and negative charges. Like charges repel each other, unlike charges attract each other. The force field showed that. And then we talked about electrical potential. The units are volts. There's all the stuff we talked about before. You probably got the notes from last time, but you can go back, and that's why I'm putting it here. It'll be on YouTube videos probably by tomorrow sometime, and you can go back and get this. So you don't have to copy all this now. You can get it later, okay? We don't have time for now, okay? This was, again, two charges repelling each other, both positive charges, and this is illustrating the electrical potential. Those are 1 Coulomb each charge. You do 1 joule of work moving at 1 meter. Okay? Here's the formula. Volt electrical potential difference, or voltage, is equal to work divided by time. Work divided by charge, work per unit charge, or energy per unit charge. Here's a slide on current. We were talking about electrostatics up till now. Now we're talking about the flow of charge. And here's Tyler. Get you on the right line. Okay. All right. What we're doing here, I'm not going through these slides because we did these on Tuesday, but the PowerPoint wouldn't work. Okay? Now the PowerPoint works fine, so I'm just letting you see these. You can go back and take notes on them later. Okay? Here's electric circuits. We actually have already done the lab with this, so you probably are fairly familiar with it. This is your circuit. This is the water analogy that we talked about before. Upper level, lower level, the pump acts like the battery. The water acts like the charge, and the water wheel is like the light bulb. Okay. The nature of current, this shows electron current always goes from negative to positive. The conventional current goes from positive to negative. It really doesn't matter which one you use. Conventionally, we use the conventional current. Okay. Current mechanisms, we talked about these, the things that the drift velocity of electron being incredibly slow, and that's part of the reason. I tried to wave my arms on that last time. Okay. More on current details. Here's what current is. It's charge per unit time, time rate of change of charge, measured in amperes, and there's Justin. Okay. These were the slides that we couldn't show last time because the PowerPoint wouldn't work last time, and I do not know why. Dimitri is here. Okay. So that's what current is. The unit is ampere. And then we got into electrical resistance. Voltage is current times resistance. That's one form of Ohm's law. You can write it a different way. Current is equal to voltage divided by resistance. Or you can write it as resistance is equal to voltage divided by current. All three ways are Ohm's law. More on the resistance. Here are the factors: the type of material, the length of material, the cross-sectional area of the material, and the temperature of the material. Now, we didn't say much about superconductors. The thing is very, very low resistance. But the trouble is they all operate at extraordinarily low temperatures. So you really spend more energy cooling them so they'll work than you save by having no resistance. So it's kind of a catch-22 there. Now, before we go into electrical power and work, I need one of these slides to give me some white space. And not a one of them is allowing me any white space. I'll find one in a minute. There one. Okay. Let's do example 6.3, top of page 152. A light bulb, get up my watch so I can keep up the time here. Okay, a light bulb in a 120 volt circuit. Now, as soon as you see that 120 volt circuit, what should come to mind? What kind of circuit is that more than likely?
Household.
Second? Household, yes. It's AC current, okay? You hardly ever run into batteries of 120 volts. I don't think you want to either. So the voltage is, and this is the weird unit, the parameter is V, the unit is V, capital V for both of them, okay? So the voltage is 120 volts. This almost sounds redundant, but that's how they do it. It's switched on, and the current of 0, so the current, what symbol do we use for current? That's a unit. What symbol do we use for current? I. I is equal to 0.50 amps, as you said, ampere. Okay? Flows through the filament. What is the resistance of the bulb? We're looking for resistance. What would resistance be? V over I. Perfect. So that would V over I, which in this case is 120 volts, divided by 0.50 amps. Can anyone do that in your head? That's, yeah, if you divide by 1/2, you're multiplying by 2. So that would be 240 what? What's the unit for resistance? Second? Ohms. Oh, okay, capital Omega, ohms. All right, any questions on that? All right, example 6.4, just below that. What current would flow through an electrical device with in a circuit with a potential difference of 120 volts again? So here's voltage is equal to 120 volts, more than likely AC, okay? Would flow through an electrical device in a circuit with 120 volts and a resistance of 30 ohms. This time they give us a resistance, and that's 30 ohms. What is the current? How do we get current?
I equals V over R.
V over R, and V in this case is 120 volts, and your resistance is 30 ohms. And what does that yield? 4 what? 4 amps, okay? And they don't mess around with significant digits on that. Make sense? All examples of Ohm's law. Many of you are probably very, very familiar with it. A few of it may be new, so get it down. We're not going to spend a lot of time on it. So, any questions? Got it? All right. Let's start finding back where we are. Okay, here where we are on page 152, electrical power and electrical work. Okay. 3 circuit elements contribute to the work. Okay? First, of course, in order to do work, you have to have energy. The energy per unit charge is your voltage. So the voltage source is essential for a circuit to do any work. Otherwise, there's no energy to expend. Next is the electrical device, which is going to use that energy. That's what we often call the load. And then the third circuit element, and these are things you remember from 2 labs ago, are your conducting wires. These maintain the potential difference across the device. The input wire is at the higher potential than the output wire. Sometimes in AC circuits we call the output wire the ground. Now I notice many of you use that terminology a lot, even for AC circuits, but most of the time we reserve that for DC circuits, but most of the time we reserve it for AC circuits. If there's no potential difference, there's no current. And I don't know if you've ever wondered about it, but you can have some pretty high voltage wires up there with basically very little, if any, insulation on them, and you see birds perched on them.
No insulation.
Huh? No insulation. Exactly. Okay? How can the birds sit on that high voltage wire?
They have higher spiritual state.
Second?
Birds not ground.
Okay, that's it. There's no pathway to ground. The bird's just sitting there. Okay? Now, if you would throw the bird a metal wire and have it catch it in its beak, immediately you have fried bird. Okay? But most birds are not trained to do that, nor would they want to. Okay? Yes, because there is no potential difference. The birds at one potential difference, there is no lead to ground, nor would you want there to be. Okay. Now, does anyone remember what the term power refers to? Second? Okay, the unit is watts. What does that measure?
Work.
Second?
Work.
Work? No, work is joules, same as energy, but it's very closely related to it. The time rate of change of doing work. Remember my backyard shoveling out the patio? Okay? Power is work divided by time. The time rate of doing work. Running up and down the stairs or walking up and down the stairs. You did the same work, but when you ran, you took a shorter time, so you had more power. You expended more power. So that's what power is, the time rate of use of work. Okay. Now, power is equal to energy per unit time. Okay, that's what power is. Now, what term or parameter in electricity deals with energy? I've just said it several times a day already. We said it right here.
Voltage.
Your voltage. And how is that related to energy? Voltage is energy per unit charge. Is W or E divided by Q. Okay? So if you had voltage, which is energy per unit charge, right? That's what volts is. Now, if you could multiply that by charge per unit time, doesn't it look like the charges would cancel out? And you would get energy per unit time, which is power. Looks like that would work. What is this quantity here? Charge per unit time. The time rate of charge.
Q.
Say again? Q is the charge. T is time. What's the time rate of movement of charge?
Volt.
Say again?
Volt.
No, volts is energy per unit charge. Watt? No, watts is power. That's energy per unit time. What is Q? Charge per unit time. Say again? Amps. You got it. Okay, that's your current. Okay? So guess what this tells you? Now this is times amps. That's equal to power. Okay? So power is equal to voltage times current. Okay? I'm going to erase this and let them write it the way they want to. Can I erase? Everybody got it? Okay. All right, here it is. Power, electrical power, is your current, which is charge per unit time, times your voltage, which is energy per unit charge. So that gives you energy per unit time, exactly the units for watts or power. Now, any of you live on your own? Okay. Every month you get a bill, probably several bills. Any of them refer to this stuff? Okay. What are you paying for when you pay for that?
Watts.
Say again?
Watts.
Okay, someone said watts.
Watts you use.
Okay. How many watts you use? I don't think so. If you read that bill closely, the unit that you're paying for is not watts. It's kilowatt hours.
You know, I don't pay bills.
Okay. But that's what you're paying for. And why kilowatt hours? Because let's go back to the definition. Power is equal to energy per unit time, right? That's what power is, what we said before, right? Energy per unit time. If you multiply both sides by time, this is measured in watts or kilowatts. This is measured, time is measured in hours. That's what you're paying for. You're paying for your energy you use, not the power. The power is the rate at which you're using energy. You're not paying for the rate, you're paying for how much energy you use. Okay, and that sort of makes sense, right? The energy you use, not the power. Even though we call it the power bill. It's not a power bill, it's an energy bill. Even though it's Alabama Power Company, yeah, they're providing power, but they're providing energy that you're using. The power is the rate at which you use it. So you're not paying for power, you're paying for energy. Okay? My grandmother even didn't call it the power bill or the energy bill. She called it the light bill. And the reason for that is, back when they first wired the houses back there, basically the only thing they were using electricity for was lights. That replaced the kerosene lanterns that got all smoky and you had to wash and clean so frequently. They were really happy to have those electric lights. They still washed their clothes the way they washed their clothes before. They still cooked their food on the wood stove. They still did everything else that they did before, but that electricity was for the lights. So they called it the light bill, yeah.
Do you remember those?
Which?
The lights like that, the wire.
I probably have seen several.
It was uninsulated.
Oh, yeah.
It was uninsulated.
Yeah. Scary, wasn't it? You didn't want to be touching any of those, okay. What's that? Oh, man. Okay.
It's
Wow.
fire hazard.
Yeah, now the fortunate thing is probably you wouldn't be grounded up there, but you wouldn't want to grab a metal pole while you're standing on that. You could be...
I always wondered about that. They were fire hazards, I guess, but that's what they did.
Well, basically they didn't use that much current either. Nowadays, with everything running on those things, yeah, the current is a lot
Then
higher.
later on, they came to some sort of ball kind or paper. I don't know what it was.
Right.
Insulation.
Yeah.
It would dry out, crack.
Yes, and then disintegrate. Right.
Thank God we're in a new era.
Yes, isn't that nice? All right, so let's see how the book handles that. Let me erase what I scribbled there. The energy bills, what you're paying for. Now, they get into all sorts of mess here. And you could write this a lot simpler than this. Energy, this is simple. Energy is power times time. So the rate is not per kilowatt. It's per kilowatt hour. That's what you're paying for. And They go through all sorts of weird ways to do this. They put the watts up here, but then they divide by 1,000 watts per kilowatt. The watts cancel out, the kilowatts go up here. Kilowatt times time is kilowatt hours, and the rate is per kilowatt hour, not per kilowatt. So let me correct that. Let me get my color to red. This is per kilowatt hour, not kilowatts. Okay? Let me get Zachary here. Excuse me. Turned out being a pretty, relatively well attended. Hopefully some more will be coming in. And there's one. Trent's here. Any others coming? Let's see. Okay. All right. So your electrical bills, you're not paying for power, you're paying for energy. Energy is power times time, kilowatt hours, that's what you're paying for. And they charge you per kilowatt hour, not per kilowatt like it says here. And this is watt hours, this conversion makes it kilowatt hours, and that's what you're paying for. Now, back when we were doing power before and energy before, what was our go-to unit for energy? Named after James Prescott. Women love them. Joules, okay. It was a joule. Why don't we pay for our energy in joules rather than kilowatt hours? That seems like an awkward unit, kilowatt hours. We could just say joules. Frankly, this is just my opinion. The power company doesn't want you seeing how many joules you're using, because a joule of energy is a tiny amount of energy. It's about, I can't remember now, millions of joules make up 1 kilowatt hour. Okay? They don't want to put that many millions of joules out. People, oh man, look how much energy we're using. We got to cut back, So they want you to see the number there in kilowatt hours. A big unit, so the number looks a lot smaller. Now that's my opinion. Maybe I'm biased on that. I am biased on that.
Most of the people that I grew up with didn't know what a kilowatt was.
Right.
They didn't know what came in.
Right. All right. I think we're getting pretty close to, yes, example 6.5. So let's see if we can find some white space to do it in. A 1,100 watt hair dryer. Okay. Let me erase that last remaining thing. Okay. Excuse me. A 1,100 watt hair dryer. Okay, what's that a measure of? 1,100 watts. What's that a measure of? Power. That's your power. Okay, and it says a hair dryer. Now, does that seem like a lot of watts? It is. Okay, and you know why? Because heat's involved. Anything that's producing a lot of heat, there is your energy drain. Right there. You're using energy like crazy.
Is that why they overheat quick?
Yeah, exactly. Okay? Hair dryers, irons, clothes dryers, water heaters, ovens, electrical ranges, oven. They sap that energy like
I
crazy.
got one daughter in one bathroom with a hair dryer, another daughter in another bathroom with a hair dryer. She goes pop it.
Yeah. Oh, yeah. Okay. Yeah, we'll talk about that in just maybe not today, but very soon. We'll talk about circuit breakers and fuses. Yeah. And that's very much involved with that. So that's a measure of power. Okay? 1,100 watt hair dryer is designed to operate on 120 volts. What's that a measure of? just like the unit says. Voltage, exactly. Okay? How much current does the dryer require? So we're looking for what?
Current.
And what symbol is that?
I.
I. So this is the unknown here. How do we relate current, power, and voltage?
P equals IV.
Okay, say that again. P is equal to IV. Is that what you said?
Yes.
Exactly. So you want to solve for current, or you want to plug and then solve for it? I don't care. Solve for it now. So what we would do is divide both sides by V, and that gives you I is equal to P over V. Your power usage was 1,100 watts, and your voltage was 120 volts. How much current did you use?
Is that 1,100 watts?
1,100 divided by 120.
9.2.
Second?
9.2
9.2 what?
amps.
Amps. Okay? And frankly, that's a lot of current. Okay? A lot of things, say in your automobile, don't you measure current in milliamps most of the time? I know in our last lab, we were all on the milliamp rate. Okay? We weren't on the amp range. We were on milliamps. Very small current. 9.2 amps, that's a lot of current. And you get to see your meter go really fast when you're using those high power hogs. Okay, so that's 9.2 amps. An electric fan is designed to draw 0.5 amps. So what's that a measure of? That's your current, I, on a 120 volt circuit. So 120 volts is a measure of, 120 volts is a measure of V, your voltage. And the question here is, what is the power rating of the fan? So what is power? You gave it to me earlier. I times V. That would be 0.5 amps times 120 volts. What would that be?
60 watts.
60 watts. About like a light bulb, okay? Electric fan, light bulbs, as long as not too major of a fan, it's going to be about like a 60 watt light bulb. Of course, most of your light bulbs nowadays are not 60 watts. They call them 60 watt equivalent. If you still have an incandescent bulb, that's going to be around 60 watts, 100 watts, something like that. But nowadays, they're using a lot more LEDs. LEDs might be 60 watt equivalent, but it may only be 5 watts or something like that. Incredible the energy saving you get from those. Of course, they're a lot more expensive up front, but the other good news is it usually takes them a long time to blow out. Okay? Incandescents are going to blow out within a few, yes.
I got an LED light that they said would last.
That what?
I got an LED light that has like thousands of little LEDs.
Right.
They said it will last like forever. It won't go out.
Yes.
It'll lose some of the LEDs, but it won't completely go out.
Right. Yeah. That's one of the best things that's happened on energy saving in a long time. Now, before that, in between the two, we had compact fluorescents, which were just like these fluorescent things, but that you could screw into a bulb, as a bulb. They were quite a bit of savings too, but I think the LEDs beat them.
Yeah, they still use them.
And then too, the compact fluorescents will go out faster than LEDs. But the other really bad thing about fluorescents in general, usually there's mercury involved. So the process of making them and disposing of them are both high pollutant potential, okay, unless you're very careful. Now, most of them were made probably in China, so China is polluting their territory, but just still when we dispose of them, if we're not careful, we could be polluting our own land. All right. 60 watt fan. Ooh, let me get this out of the way. Oh, I think we've already done those slides. Okay. All right. There is a nice little table. I wish they would have put it in the PowerPoint. They didn't, but this is on page 154 of your text before you get to magnetism. And this table relates to a lot of these things we're talking about. Charge is basically a measure of how many electrons you're talking about, or equivalent electrons. Q is the unit for charge. Is the symbol for charge. N is the number of electrons times electrons. Coulomb is the unit for charge, and it takes about 10 to the 18 electrons to make 1 coulomb of charge. Electric potential is your voltage, that's work per unit charge, and that's measured in volts, joules per coulomb. Electric current is I, that is charge per unit time. Amperage is coulomb per second. Okay. Electrical resistance is voltage per unit current, volts per amp, and that's an ohm. And electrical power is watt, and a watt is joule per second, just like the other one. Now, there's another little blurb here, concept applied on shocking cost, that plays on words there. It's not really all that shocking. You can predict the cost of running electrical appliance with just a few calculations, and you can play with that if you want to. You might find it enlightening. Okay? The people behind the science here, I'm not sure most of you would recognize this guy as a scientist, Benjamin Franklin. Most of you probably think of him as a statesman. You know, yeah, very much a scientist. But he was one of the big five authors of the Declaration of Independence. He was on the Constitutional Congress. He was part of that. He was a Postmaster General, but he was also a scientist and an inventor. He invented the Franklin stove. Second? Oh, yeah, okay, I'd forgotten that. Bifocals.
Electricity.
And yes, he was one of the early scientists in electricity. You're absolutely right.
Because I just remember when he got
The
the kite and the key, and you just trying to fly it to get to the lightning hits it.
Exactly. Quite a shocking experiment, but he was safe with it, and fortunately lived to talk about it. Okay? So that's Benjamin Franklin. All right, bottom of the page, before we get to magnetism, one more, two more examples. Let's hit those. Sorry about this. Clear my screen here and hit this. All right. Yes, I do, but I'm in the, yeah. Okay. Can you pick it up at the end of class and not interrupt class? Okay. All right. Example 6.7 on page 155. Then we'll do 6.82. What is the cost of operating a 100-watt light bulb? So what's that a measure of? That's your power. Okay. 100-watt light bulb for 1 hour. What's that a measure of? That's your time, okay? If the utility rate is 10 cents per kilowatt hour, the rate is 0.10, yeah, a long time ago, per kilowatt hour. I was just going to say that, okay? Because, now I remember shortly after we moved to Birmingham or Alabama, that Alabama Power was bragging that they had low cost electricity around 7 cents per kilowatt hour. It's lower than the national average. I haven't seen those kind of brags lately. I don't know what they're up to now. Is it more like 20 or I don't remember. Yeah.
You know, that's my area here is on TVA.
TVA.
Yeah. Not Alabama.
Right. And it's probably a little cheaper or a lot cheaper, do you know?
Cheaper. Right. I'm not on it, but I know that.
Yeah.
My neighbor is.
Yeah.
I'm sitting there thinking, right in the middle, nowhere near TVA. You know.
Right. But they're on it.
They're still there.
My parents-in-law live in Huntsville, and I'm pretty sure they're TVA up there. I know they didn't like being on. They had a place at Smith Lake that was on Alabama Power, and they really fussed about that because they liked TVA so much better. But anyway, so here's what we got, 10 cents per kilowatt hour. Okay? What is the cost? So we're looking for cost. Well, you know, units are your friends here. So all you have to do here is look at your units. Well, here you're given watts. We need it in kilowatts. So what do we have to do to make that 100 watts so many kilowatts? Move your decimal. How many? 3 places to the left. That makes a kilowatt. So this 100 watts of power is 0.100 kilowatts of power. Okay? Then you take your kilowatts, multiply it by your 1 hour. I didn't put my units in, should have. So that would be 0.0, multiply that by that, 0, no, I'm sorry. I got carried away here. Okay. I was doing my final answer. Not yet. That would be a tenth of a kilowatt times 1 hour would be a tenth of a kilowatt hour. Okay? Okay? And then you're being charged at 10 cents a kilowatt hour, so the cost would be 0.10 per kilowatt hour times 0.100 kilowatt hours. They cancel out, and that gives you $0.01, which is 1 cent. Now this is in the old days. Okay? All right. I know you're in here. I will find you. 100, right? Okay. Has anyone else come in since I called roll? There's been so many people coming and going, I'm afraid I might miss somebody, but hopefully I've got everybody. Okay? Now, 1 penny on that rate. I don't think we're doing 10 cents a kilowatt hour anymore, so it's going to be more than a cent now, but that's how much to do a 100 watt bulb for 1 hour. But of course, if you're running that bulb for 8 hours, that's going to be 8 cents, and that's only for 1 day. And if you do it 30 days, then it's pretty cheap. Okay? 30 days times 8 cents would be $2.40. So a 100 watt bulb, that's not your big energy draw. It's the heat that's your energy draw. Clothes dryers, heating elements, you know, in your stove or in the AC system, whatever, heat pump system, that's where your energy is used. All right, so that was 1 cent. Okay?
That's probably 1934.
Yeah, that was a long time ago. All right, example 6.8 then is an electric fan draws 0.5 amps. We had that before. Okay? In a 120 volt circuit. So this is your current. In a 120 volt circuit, that is your voltage. Okay? What is the cost of operating the fan if the rate is 10 cents per kilowatt hour? So again, the rate is 10 cents per kilowatt hour. Okay? Now they say, what is the cost of operating the fan? They don't tell you how many hours, so this is going to be cost per hour. Okay? So basically what you do, again, your units are your friends. Here we have voltage and here we have current. What do those give you if you combine those? Voltage and current. Okay, if you divided them, they'd be ohms. But we're not dividing here. We're trying to get watts. How do they relate to the power? Anybody? Power is? Anybody? IV. Okay. So your power is I times V, and that would be 0.5 amps times 120 volts. We already did that once before. That's 60 watts, right? How many kilowatts is that? 0.060 kilowatts. Multiply that by your rate, which is 10 cents per kilowatt hour. Now this is kilowatt hours because you multiplied, no, I'm sorry. You're going to be getting per hour, okay? So multiply that, 0.10 per kilowatt hour times 0.060 kilowatts. And what you get, the kilowatts go out, and you get 0.006, 0.6 of a cent per hour to run a fan.
Is it okay that I'm just taking 0.5 and multiply by 120 and then 0.1 and over 1,000?
Yeah, you can do that too. That's how the book does it. Yeah, perfectly fine. I just go on and move the decimal rather than doing over 1,000. So.
I find it.
If you find it easier to see.
Decimal, I'd probably mess up.
Okay, yeah, and that is I see it happen a lot. So yeah, not a bad idea to do. Okay, but 0.6 of a cent per hour, that electric fan. Again, not you. Yes.
So that's 0.006 hours.
This is cents per hour. Per hour. So if you wrote that in pennies, that would be 0.6 of a cent. 0.6 cents per hour. Very, very inexpensive. At that rate. We're not at that rate anymore. We're much more expensive than that these days. Okay?
Whoa, wait a minute. You said 0.006.
That's dollars.
Oh, okay.
That's dollars. And if you go to cents, move this two places that way. You get
Okay.
6
I
cents.
couldn't interpret that.
Yeah.
I didn't know what that. It kind of looks like an M.
Yeah, making fun of my writing now. I don't mind. It doesn't hurt. No, I'm just kidding. Okay. Okay. All right.
Everybody else seems to know.
Yeah. All right. So that's the last of the electrical power and work. Now let's move to magnetism. Now this isn't the first. I say the chapter is split into two pieces, electricity and magnetism. The electricity is the first part and it's the bigger part, but we're now going to deal with the magnetism part. Brian's here. Frankly, just barely, okay? Because, unfortunately, I've got to leave in about 10 minutes. Yeah, so, but you can, yeah, so, glad you came. Okay. All right. So let's talk about magnetism. Now, we said with electricity, the earliest they knew about electricity was, the parlor games. Rubbing amber with fur or something like that, and shocking your friends and making people yell and stuff like that. Boy, what fun that was back then, okay? But that's all they knew about electricity. Way before they knew about electricity, they knew about magnetism. How? Anybody have an idea? There's naturally occurring magnets. You remember what we call that mineral? The common name is lodestone. Okay? The actual mineral name is magnetite. And the unusual thing about that is hematite, which is the normal iron mineral, and magnetite, chemically, they are absolutely identical. You can't tell any difference between them. The only difference is magnetite is magnetic and hematite is not. Okay? So naturally occurring magnets, the mineral is called magnetite or lodestone. Yes?
Is that available? Could we go out in the woods and find that here? I doubt it.
I don't want to say you can't, but it would be very
Well,
unlikely.
it says it comes
Yeah. But
magnet.
people do find it, and it is magnetic. So what was the deal with having a magnet? Any practical use?
Well, they made a compass.
Compasses, exactly. In the old days, that's the only way they had to guide ships at sea, was with a compass. Yeah, and then they shot the stars to check on that. But while in the daytime, no stars to shoot. Now, they did shoot the sun at noon, and that would give them some ideas. But basically, the way you navigate anywhere, in the woods or anywhere else, you use the compass. Because left to your own devices, people tend to go around in circles. You know, if you're out there alone, unless you're really good and have a great sense of direction, people tend to move around in circles and do that kind of weird things. Okay, so associated with naturally occurring magnetic materials, lodestone is a common name, magnetite is the mineral name. Now, magnetic materials, if something is a magnet, it always, not just sometimes, always has two poles. Okay? Now, electric charges, there are two charges, right? There's positive charges, there's negative charges. Okay? But guess what? You can have an isolated positive charge, no sweat. You can have an isolated negative charge, no sweat. You cannot have an isolated north pole of a magnet. Let's say you had a bar magnet here, and if you put it under a piece of paper and sprinkled iron filings on top, you see all those iron filings run to the poles, okay, and hardly any in the middle. Well, couldn't we break off one of those poles and then isolate that north pole? No. As soon as you break it, this end that didn't attract any iron filings before suddenly becomes a south pole. This one becomes a north pole. Okay, and you have another magnet. Magnets are always dipolar. Sometimes people say bipolar, but they don't have that illness. You know, but they're bipolar. Okay, I mean dipolar. Yuck, I just said it. Okay, dipolar. Okay, now here's another feature of magnetism. There's only 3 naturally occurring magnetic materials. There are 3 metals: iron, cobalt, and nickel. And I don't know if you find this coincidental. I don't. There's a reason for this. If you find those 3 on the periodic table, here they are. Number 26, iron. Number 27, cobalt. Number 28, nickel. All the rest of the metals to the left of iron, not magnetic. All the to the right of nickel, not magnetic. Tons more metals out there, only those 3 are magnetic. Now, they do things with them, like making alloys and things like this, so you can come up with other materials that are somewhat magnetic, but those, you basically got to have 1 or more of those in it. Now, cobalt is not a very common mineral, okay, or metal, so it's mostly iron and nickel. And just for your general information, iron makes what they call soft magnets, easy to charge or make magnets, but also easy to lose the magnetism. Nickel make what they call hard magnets, which are very hard to produce, but also very hard to lose the magnetism. So it's not that one's harder or softer than the other, it's just whether the magnetic, how easily you make or destroy the magnet. These 3 are called your ferromagnetic materials. By the way, ferro, that basically means iron. Okay? If you look at the periodic table, Fe is iron from ferrous. Okay? So the magnetic materials are iron, nickel, and cobalt. Now, they knew about magnetism way back. They used magnetism for forever in a positive sense, not just playing games with it, actually using it. But no one really understood how it worked, or even why it worked. Nowadays, the modern view is associated with magnetic fields. Just like we talked about electric fields, anytime you have electric charge, you have a field around that charge. What direction is that field convention is, if that's a positive charge, which way is the field lines going? Away from a positive charge toward a negative charge. We use the same type of convention here. The field lines go away from the north poles toward the south poles. You have to have a field line always have directions, so that's the convention for the directions. Electric charges, electric field lines from positive charge to negative charge. Magnetic field lines from north poles to south pole. The field lines are there, they have a direction, that's the convention for the direction. Okay. I hate to do this to you because I feel like I'm cheating you out of your tuition dollars, but I'm afraid we're going to have to call it quits. We probably don't have time quite to finish this slide, so sorry about this. I explained to the folks who were here earlier. Yeah, boy, they're protesting like crazy, okay? Walking out on us, okay. All right. Have a good weekend. We'll see you Tuesday. Get back on regular schedule Tuesday. Yeah, Zachary, did you need something? Okay, what's this?
I need the last one.
The last one? Okay. That's one reason I quit a little earlier than I was, because I knew some of you needed things.
And
I need to leave by 4:30.
Your hours on Monday are 2 to 4, right?
2 to 4. No, 2 to 6.
2 to 6.
Wednesday is 2 to 4.
Okay, because I still got to take test 3 and 4.
Okay. All right. Now, what are some of the things you need?
The last lab. I don't know which one it is. It's called.
Okay.
What it's named.
It's the Ohm's Law lab.
Yeah, yeah.
Okay, you need that too?
Yeah.
Okay.
I think I just saw it because it looked like it had some like tube thing.
Here we go. Ohm's Law. Who needs that? Ohm's Law.
Have a great
Thank
weekend.
you.
Huh?
Have a great weekend.
Okay, thank you. Lab 5. Is that the one you said was just energy?
Yes, sir, I believe.
Okay, it's not actually Lab 5. Is that the one you need?
Yes, sir.
That's the one.
Yes,
Okay.
sir, thank
It
you.
says Lab 5 on it, but it's actually, I think, Lab 6 or something like that.
Thank
But,
you.
yeah.
Thank you. And you have a great weekend.
Okay, you do too. Thanks. All right, good deal. I know you're caught up with everything, so you got the only one with the paper turned in yet, so way to go. Huh?
I just realized that I got a 90.
What's that?
Oh, I just know I got a 90.
Yeah, on the paper. Yeah, good job.
Thank you.
All right. Sorry I had to leave early today, folks.